second session of FSOSS 2014, Day 2. I'm very pleased to have Tom Stellard of AMD. He's a senior software development engineer there, and he's been actively involved in the MESA 3D and LLVM projects over the last 3 or 4 years, and is currently working with OpenCL, compilers, and so forth at AMD here in Toronto. Thank you, Tom Stellard.
Thanks, Chris. Okay, so like Chris said, my name is Tom Stellard. I'm a software engineer at AMD. I'm on our open source GPU driver team, and today I'm going to talk a little bit about the open source drivers we develop, what they are, what you can do with them, and how you can help improve them if you're interested. Okay, so I'm going to start just by giving a brief overview of our drivers, and then I'm going to talk about the different projects that we contribute to. Our drivers are actually made up of a whole bunch of different projects, so it's not just a single project that we are contributing to when we're working on these drivers. I'll talk a little bit about some applications and different things you can do with our drivers. I'll go briefly over the architecture, and then talk a little bit about what you can do if you're interested in getting involved. Right. So before I get started, I just want to clarify one thing that can be a little bit confusing. So on Linux for AMD GPUs, there's actually 2 completely different drivers that you can have. So one driver is called Catalyst. You may also see it called FGLRX, which is the name of the kernel driver. And that is a completely closed source graphics driver. And that driver is a completely separate and a completely different code base than the open source driver. The open source driver, typically, you might hear it called Radeon after a kernel driver. You might hear the term Galleon driver, Mesa driver. Those are open source. And so what I'm going to talk about today is the open source driver for AMD. So the open source drivers, they support GPUs going all the way back to the old RAID GPUs up through our latest offerings. And you may think it's a little strange that we support such old GPUs, but the reality is that people use them, and we actually have had someone submit patches several months ago for these. So people are out there, people care enough to write patches to fix bugs, so that's why it still works with our driver. And the development of these drivers is actually a collaborative effort. It's not just AMD doing all the work. We do have our open source graphics team at AMD. But in addition, different operating system vendors like Red Hat, OpenSUSE, Canonical, they make a lot of contributions. And also we get a good number of independent developers. So these are people who may work on in their free time. Maybe they have a game they want to go faster. Maybe they have a game that doesn't render something correctly and they want to fix it, so they make a contribution. And so we actually have good numbers of independent developers. One thing that's actually really great about the open source drivers is they're part of the default install in most distributions. So if you go download your, say, Ubuntu ISO from the internet and install it on your system, the open source drivers are right there. So as soon as you boot it up, you can do OpenGL, all kinds of other things. So it's really easy to get started. All right. So I'm going to talk a little bit about the projects that we're involved in developing these drivers. So the first and sort of the core project is the Mesa project. What Mesa is it's a project to bring OpenGL functionality to Linux. Now, if you aren't familiar with the 3D stuff, OpenGL is a cross-platform API that allows you to do 3D graphics. So there's implementations on Windows, Linux, Mac OS. And the idea is you can have this common API, so if you want to port your code, it's a little bit easier to move from operating system to operating system. So Mesa we first started way back in 1995. It was a software-only library, so all the OpenGL functionality was implemented in software and all running on the CPU. As Mesa became more popular and people started to use it and actual 3D hardware was starting to be produced, people started to add support for actual hardware acceleration. So a number of different hardware drivers were implemented, and the project kind of grew, and it even grew beyond just doing 3D to other GPU-related APIs like video encoding, general purpose computing. And so it really has grown into a large project that can do a lot of things. So in terms of the hardware that's supported by Mesa, there are several different what we call user space drivers that Mesa supports. So if you're familiar with, I don't know if you're familiar with the terms kernel space and user space, but there's sort of a distinction between the two when we talk about drivers. So we have our kernel drivers, which are in the kernel, and then the user space drivers, which are in user space communicate to the kernel. The user space drivers are in Mesa. So of course we have drivers for AMD GPUs. They're also drivers for Intel GPUs. And these two drivers are really the most mature of the drivers in Mesa. Both AMD and Intel actually fund employees to work on these drivers. So they actually see a lot of development, and they're pretty good quality. There's also open source drivers for NVIDIA GPUs. Now, unfortunately, NVIDIA doesn't really contribute anything to the open source efforts, so all these drivers are engineered using reverse engineering. So all the information they get in order to figure out how to program the GPU is done by reverse engineering. And they've actually made a lot of really good progress and done a lot of neat things, but still have a ways to go to sort of match the other drivers. Another reverse engineering effort is a driver called FreeDreno, which is for the Qualcomm Adreno GPUs. And this is something that actually Red Hat is funding a developer to work on. So it's kind of an interesting project. The most recent addition to Mesa was a VC4 driver. And so VC4 is for the Broadcom GPU that's used in the Raspberry Pi. So it's an actual open source driver that you can use on the Raspberry Pi. It's still in its early stages, but I think it's a very cool project because up to this point, Raspberry Pi has used closed source proprietary GPU. So I think it will really help to kind of build that ecosystem even more. In addition to different hardware accelerated drivers, there are still some software rasterizers. So there's actually two, soft pipe and LLVM pipe, which we'll talk a little bit more about later. Okay, so another project that we're involved in are different display server projects. Really, X is kind of our focus right now. That's probably what everyone is using for the most part on their laptops. So what a display server is it's basically the sort of common underpinnings for your window managers, whether you're using GNOME or KDE, all that kind of sits on top of X to sort of manage the low-level stuff. And in X, it's split into two sections. So you have your X server, which is device independent, has all sort of common code that can be used by any different kind of hardware. And then there's a portion that we call device dependent X, which you can write hardware-specific routines in to get better performance to make use of different hardware features. So we're involved in both of these. In addition, there's another project that's part of X that used to be on its own called Glamour. And what Glamour does is it provides 2D acceleration in X using OpenGL. So it's actually kind of cool project. Now it's upstream in the X server tree, and it's something that we've been contributing to as well. So besides X, there are actually other display server projects that have started in the last few years. You may or may not be familiar, but there's Wayland and Mir, and these are seen sort of as like the modern version of X with some more modern features, and still, everyone, for the most part, people use X, but these are kind of up and coming. They're really interesting projects, so it'll be interesting to kind of see where they go in the next few years. Okay. And of course, another project we're involved in is the Linux kernel. So we have our kernel driver, which is called Radian, and basically what it does, it just provides an interface to the user space driver, which is in Mesa, to talk with the hardware. And the kernel driver, it does things like hardware initialization, memory management, sort of low-level stuff like that. And in addition to the Radian driver, we are working on a new kernel driver called AMD GPU. And this is meant to be a unified kernel driver. So the idea is that we have a single open source kernel driver, and then we can either use the Mesa open source user space on top of it, or we can use the Catalyst closed source user space on top of it. I'm not going to go into a lot of detail about this in this talk, but if you're interested in finding out more about this driver, Alex Duiker did a really good talk at XDC 2014, so I encourage you to go check that out. And yet another project we're involved in is called LLVM. LLVM is a reusable compiler library, and it's actually an umbrella project with several sub-projects. So you have LLVM core, which defines an intermediate representation that's supposed to be sort of like an assembly language that's generic, that you can write and compile to code on a number of different systems. The core also has optimization passes for this IR, and then code generation. So you can generate code for x86, PowerPC, our AMD GPUs, there's a lot of targets that are supported. Another sub-project is Clang, and this is a compiler front end for C languages, so C, C++, Objective-C, OpenCL-C, and CUDA. So when you kind of put Clang and LLVM core together, you actually get a full compiler. So you may have heard of Clang before, and this is what it is. It's kind of these two projects working together. But because it's a reusable compiler library, you can kind of, you can pick and choose parts. So for example, in our driver, we really just want, especially for GLSL in OpenGL, we just really want the code gen. We aren't using it for doing the lexing and the parsing. So we can just pull that part out of the library and use it in a project. So it's kind of a cool thing. Another LLVM project is called libclc, which is an OpenCLC built-in library. And so what built-ins are, so OpenCL is sort of an API that allows you to do general purpose computing on the GPU. And it has a number of built-ins, which are things like logarithms, or taking the tangents of angles or whatever. So there are all these built-in functions that are implemented, and you need a library to support these in order to run your application. So that's what libclc is. All right, another project we work on is called Piglet. We use this for driver testing, and Piglet, it's really split into two parts. There's a test framework, which consists of test runners, facilities for doing report generation, either in HTML or other formats. And then there are actual unit tests. So we have unit tests for OpenGL, OpenGLES, OpenCL. And it's actually a really good and really easy to use test suite. It's very customizable, and it's really easy to integrate external or third-party test suites into the framework, so you can make use of all of the sort of nice report generation it has. For example, I've been doing a lot of work with a computer vision library called OpenCV, and I was able to integrate their test suite into Piglet, and now I have these really nice HTML displays that I can look at. So again, another cool open source project that we work on while developing our drivers. Okay, so those are all the projects. Now I'm going to talk a little bit about what you can actually do with our open source drivers. I think that's probably what everyone's really interested in, no matter what your background, whether you're a developer or just kind of a user. So of course you can do 3D graphics with our open source drivers. So if you have an OpenGL 3.3 application, for the most part, you can use it with our drivers. There's a number of open source games. There's some Steam games you can use in our drivers. And these aren't by any means complete lists. These are just ones I pulled off of either bug reports or things that I've heard people tell me they use. But there's actually, for the most part, things should work. And if they don't work, there's probably a bug. So please file a bug if you find one. In addition, OpenGLES 3.0 applications you can run with our open source drivers. And also you can use Wine. If you're not familiar with Wine, Wine is a compatibility layer for Windows applications that allow you to run them on Linux. So traditionally how Wine works is so let me back up first. On Windows, most or a lot of 3D games and 3D applications actually use an API called DirectX, which is it's the same idea as OpenGL, but it's a different API. So in order to support these applications via Wine, you have to translate DirectX to OpenGL, and then you can make use of the drivers, because there's up to recently there was no DirectX native library on Linux. But recently some people have been working on this, and they actually developed a DirectX 9 library, so you can now get native DirectX support using Wine, and it really brings a pretty big speed up to applications, because you can get rid of the translation layer, and it enables a lot of really cool things with open source drivers. Another thing you can do with our drivers is hardware accelerated video decoding and encoding. So on our GPUs, we actually have dedicated engines that can do decoding and encoding completely in hardware. So all the decoding algorithms are actually implemented on the chip in hardware. So for video decoding, we have UVD. For video encoding, we have VCE. These are the names of the engines. And doing the decoding in hardware really helps reduce CPU usage and power consumption, because you're basically offloading these tasks onto the GPU, and the GPU is designed specifically for these kinds of tasks, so it can do it really efficiently, and it really makes a big difference as far as power. And I have just a little example here to demonstrate. So here's a screenshot. You can all, yeah, this is pretty big. Okay, this is a screenshot of an HD video running on my system, and I have the top going with the CPU usage. You can see, in order to decode this video, it takes about 88% of the CPU. And this isn't a small CPU. This is on a system where the cores are clocked at 4 gigahertz. So it takes a lot of CPU power and also energy to decode this video. So if I were to run the same video using our UVD engines, as you can see in this picture, the CPU usage has dropped dramatically down to 1.7%. Actually, most of the player actually isn't really doing a lot. Pretty much all it's doing is waiting on the engine to return the encoded frame. So you can see you get much less CPU usage. It makes a big difference in power savings, and it's a really great feature of our drivers. So in order to make use of these specialized hardware decoding and encoding engines, typically you have to use a higher level API. So there's a number of APIs that we support in our open source driver. One is called VDPIU, the Video Decode and Presentation API for Unix. So in our open source drivers, we support decoding MPEG-2, MPEG-4, H.264, and VC1. And these are all done via the UVD engine on chips that actually have a UVD engine. And for players, MPlayer supports this API, MPlayer 2, MPV, VLC, and even Flash supports this API. So with the open source driver, you can actually get hardware accelerated video playback using Flash, which is really cool. Now it's not enabled by default, you have to update a config file, but it can be done, and it's actually something that's very cool. Another API that we support in the open source driver is VA API. VA stands for Video Acceleration. Again, for decoding, we support MPEG-2, H.264, VC1. We're working on MPEG-4 support. Again, accelerated via our UVD engine. And the players that support VA API are MPV, VLC, and then there's GStreamer plugins as well. So one more decoding API is called OpenMax. And this is basically just an accelerated multimedia API. It actually does decoding and encoding. And it's a Chronos standard. So Chronos is an organization that standardizes different APIs. OpenGL, as I was talking about earlier, is actually a Chronos standard. And there's a number of other standards like OpenGLES, OpenCL, lots of things that Chronos works to come up with a standard definition of the API. So on our open source drivers, the features we support in OpenMax are MPEG-2 and H.264 decoding, and also encoding H.264. And again, it's all hardware accelerated. Even the decoding on our C islands and newer uses our VCE engine, so you can get hardware accelerated encoding with OpenMax and get the same sort of reduced CPU usage and power savings as my example with video decoding.
You said C islands only. What? I know kind of what that means, but do you want to say it so everybody else knows?
Well, when people ask me that question, usually I point them, we have like a decoder ring on our wiki. It's really hard for me to tell for sure what there's like HD. I don't know, Tim, if you have any sort of tricks for remembering that.
I use Wikipedia.
Yeah.
That's fine. I don't mean to.
Yeah, I mean, we generally work internally with engineering code names. So we talk about, and a lot of websites talk about them, but we talk about products like Kaviti, Kaveri, for example, which are C islands. The marketing people take them and rename them A6, A8, A10, and Radeon HD, whatever. They don't often mean a lot to us. Those names, and that's why we go, when we get bug reports on a Radeon HD whatever, we usually go to Wikipedia and go, okay, what's a Radeon HD whatever? Oh, that's a Kaveri, okay.
Yeah. So, yeah, Wikipedia is a good resource.
Does AMD contribute to Wikipedia?
Yeah. There are people who correct, sometimes those things on Wikipedia, but those products are wrong and we correct them.
It's just another open source contribution.
Absolutely.
Yeah. We actually have our own wikis too, like through the X.org Foundation. They host wikis, so that we have. There's actually a page called Radeon Feature, and we have similar information about what maps to what. Okay, so other things you can do with our open source drivers is GPGPU, which is general purpose GPU computing. So basically what that means is you can take, programs maybe written in a C-like language and actually execute them right on the GPU. It's used a lot for scientific simulations, in computer vision, and there's certain applications where you can get a big speed up by running your programs on GPUs using the parallel processing power that they have. So with our open source drivers, we have something called Clover, which is an OpenCL implementation. It right now has partial support for 1.1. One of the really neat features about it is it allows you to do headless compute, so you can actually run OpenCL programs without having an X server running. So if you have a server or some other headless system, you don't need to actually even install X at all, which is really nice. So I mentioned before I've been working with OpenCV. It's mature enough to pass about 95% of the test cases of OpenCV, which I think is a pretty solid test suite, so it's making pretty good progress. In addition, I talked a little bit before about libclc. So kind of the current status of that is it provides implementations for both AMD GPUs and also PTX, which is an assembly language for NVIDIA GPUs. So the idea is you program in an assembly language and you pass it into NVIDIA's proprietary driver and it will run the code. So both those are supported. And what we're working on now is we're actually, just maybe a month or so ago, we released all the built-in implementations from our proprietary driver. So these are the ones that are used in our closed source Catalyst driver, and they're all conformant implementations. They passed all the conformance tests required by the spec. So these are now open source. We've been working on porting them into libclc so that they can be used by more people in the community. That's what you can do. So I just wanted to give a little picture, sort of what our driver looks like and kind of how it works internally. So I'm going to start over here on the right. So let's say you have a 3D application, like a game or something like that. How that works is that uses Mesa, which has OpenGL and the user space drivers, and so it'll communicate with Mesa. Mesa talks to libdrm, which is a user space library that's kind of a wrapper around our kernel interfaces, and then libdrm talks with the kernel. For 2D applications, and 2D applications are things like maybe Windows in your window manager, or you have a web browser and you're scrolling text. Those are sort of the 2D applications I'm talking about. So for those communicate with the X server, because the X server is sort of in charge of managing, like I said before, if you have a desktop environment, it's sort of the underpinnings for all of the stuff that is being displayed. So those 2D applications talk to the X server, and then the X server can really, for accelerating and implementing some speed up and other things on the GPU, it really has two different things it can do. The first thing it can do is it can use, as I mentioned before, the DEX, which is hardware specific. So in there you have it, hardware specific routines to implement, rectangle copies or whatever to get better performance. Another option it has is it can use something called Glamour, which I also mentioned before. And basically what all this does is it translates the 2D acceleration commands into 3D, and then it uses the Mesa driver. So this way you don't need to implement a separate 2D driver. It's less code that you need to maintain. It's a very nice feature.
So,
yes?
I've always found this stack rather confusing. Where does compositing happen? I would have said an XOR server, but then you miss all the 3D stuff, so that doesn't make sense to me.
So for X, compositing is not done at the server. It's usually a function of like your window manager will take care of that. In those other display servers I talked about, like Wayland and Mir, those actually do the compositing right in the server.
So let's say you have a Mesa window. Where is the compositing done in that diagram?
Okay, so Mesa, so the 3D application, it's sort of a separate, the 3D applications are really communicating directly with the 3D driver. So they're just basically given a window or something and they're drawing on it. Any sort of compositing or those kind of like things, those are really things that have to be managed by your window manager, like GNOME or KDE or whatever. I'm not sure what the specific, I know there's like, I forget what they're actually called in those, but that's more handled. So that would really be, I guess that would sort of be like a 2D application that you're using to do the compositing.
So maybe I'm using the wrong word.
My understanding, Tom, is that they do a read for X, they have a regular X window, 2D window, right?
Yeah.
The window managers do a redirect, so that surface is available as a 3D surface, and the compositing is done with 3D.
Yeah, I mean, you might be right about that.
There's some kind of a GL extension that does that, where you know, the application is using X calls, it thinks it's drawing to a regular, using normal X calls, but that's redirected to a 3D surface and then composed in OpenGL on this side, right? So it's not really shown.
Okay.
In this picture.
Yeah, I guess it's probably, you know, if you go on Wikipedia, there's some more complicated and probably more informative diagrams that might be more helpful. All right, so I'm just gonna talk really briefly about the architecture within Mesa, because this is sort of the core of the drivers and where a lot of the development happens. So within Mesa, we use something called Gallium, which is a framework for writing GPU drivers. It's part of the Mesa source tree, and there's two main components. There's a state tracker, which is basically like an API implementation like OpenGL. There's something called a pipe driver, which is a device-specific driver implementation, and then there's a WinSys, which is operating system abstraction layer. And all Mesa drivers use Gallium except for the Intel drivers and the older Radeon drivers. So it's sort of the framework that most people like to use. So here's it. So again, this is sort of zooming in on the Mesa picture. So this is how it's organized. Like I said, state trackers are sort of the top layer. These are where the API implementations happen. Then below that, you have the Gallium driver, which has a pipe driver, which is actually operating system independent, and then the WinSys, which is the operating system abstraction layer. So one of the really nice things about this design is it makes it really easy to reuse code. Because if you want to add support for a new API, you just add a new state tracker and you're able to reuse the existing pipe driver implementation. Or if you want to import the drivers to a new operating system, all you would have to do is implement a different WinSys, and you could reuse all the API and the pipe driver code. So it's actually kind of a really, really good design, and you know, something that's made it really easy for us to reuse code and support all these different APIs with a relatively small number of developers. So these slides, these just go into more detail about Gallium. I think I'm just going to kind of skip over them for now. But these will be posted, so if you want a little bit more information or maybe a refresher on some of the things I've talked about, these slides will be in there if you want to take a look. Okay, so I'm going to talk about how you can get involved if you're interested in helping out. So this is a question I get a lot. People always ask, oh, like I really want to get involved in GPU driver development, like what can I do? And the best thing I can say is find something that you're interested in to work on. So whether that's a game that you want faster, or maybe there's a bug in a game you want to play, or maybe you really like compilers and you want to write some great new optimization. Whatever the case may be, find something that interests you to work on, because it's a lot easier to get motivated and it's a lot easier to stick with it if it's something that you're interested in. And there's really a lot of things that people want to get involved can do besides just coding. There's testing, you can report bugs, you can do performance analysis, you can actually help package the drivers for different distributions. So we actually have a lot of community members who will package the most recent versions, maybe snapshots from our Git tree for Ubuntu or other distributions. And then people can easily install the latest drivers without having to compile from source. So that's something that is one way to get involved. The other thing that people can do is just go on our IRC channels and answer questions for people. Yes?
A really important neglected contribution is documentation.
Right. Yeah, and that would be helpful for sure. If someone wanted to come along and add documentation or fix our documentation, yes, that would be very nice.
Cash prizes? No.
Yeah. And one of the really cool things about working on GPU drivers is there's kind of something for everybody. So if you're interested in 3D graphics, you can work on the Mesa drivers. You can work on the Mesa State Tracker, which is where OpenGL is implemented. You can work on the brand new, we call it 9 State Tracker, which is the DX9 implementation. So there's a lot of cool stuff for 3D graphics that you can work on. If you're into compilers, there's lots of opportunities. We have a full LLVM backend to generate code for our GPUs. So that's something to work on. There's a GLSL, which is a shading language that's kind of like C, which is part of Mesa. You can work on that. You can work on Clang. If you're interested in GPU, you can work on Clover, which is our OpenCL implementation. You can write a new state tracker if you want. I mean, there's lots of other GPU APIs out there. You can come up with your own, and there's lots of stuff that you can do with our open source drivers. And also, if you like operating systems, there's lots of areas to improve the GPU memory management, and also GPU scheduling algorithms. That's something that hasn't really been looked at too much. So there's lots of opportunities for people who are interested to work on different things. Okay, so if you do want to get involved, the first thing you need to do is install the drivers. So the easiest way to get the drivers is use what are packaged by your Linux distribution. So as I said earlier, most distributions package the drivers by default. So it's relatively easy to install some version of the driver. The only thing is, most of the time distributions, they only package stable versions. So these might be 6 or 7 months old versions of our drivers. So they don't always have the latest features, the latest optimizations. There are actually some distributions, like Gentoo, for example, they do have packages that will pull right from our Git tree and allow you to install the latest drivers easily. But for other distributions, if you want to get the latest version and do some hacking, you need to install from source. And this really isn't as difficult as people think. So I just have a few tips here for anyone if you're interested in building or getting started with a project. And again, these slides will be posted, so if you want to refer back to this later here, you can. So start with Mesa. That's kind of the core of our drivers, and that's where, for the most part, changes are made. So if you're new to the project, that's probably the most likely place that you would be making changes. One thing you can do to make the build from source a lot easier is if your package manager has a feature to install build dependencies. So in Ubuntu, you can use apt-get build dep, and what this will do is it will install packaged versions of all of the dependencies you need to build a package like Mesa. So then all you have to do is build Mesa from source. You don't have to go around and download all of the dependencies from source, compile it on your own. So it's a nice way to get started. Another tip which seems obvious, but read error messages from the configure script. Use Google, type things in. You can get a lot of help that way, and it's pretty easy. Another common issue is that people forget to update their library path when they install the drivers. So like most projects, when you install the drivers, they go into user local, which may or may not already be in your path. So you might try and run your application, and it can't find the newly installed shared objects. So you have to make sure that you do that. And again, the more difficult things to build, like the kernel and the X server, usually those aren't really required. So I always recommend, start with Mesa, build it, and ask questions. And if someone says, oh, if you want to make that change, you have to install an upgraded kernel, or you have to build X server, then go ahead and do that stuff. But it's a good idea to kind of keep it simple when you're first starting out. And then here's just some extra information if you want to get involved. There's a number of mailing lists. IRC channels, we have some to-do lists out there if you're looking for a starter task. There are lots of avenues if you have some questions to ask. And then here are source code repositories. This will be useful if someone wants to look at this later and know where to get the latest code. Okay, so that's pretty much all I have. Does anyone have any questions about our drivers? Yes?
You seem to be doing a lot of open source stuff. Why does the Catalyst driver for Linux still exist?
I think the answer to that question is sort of like most business questions, it's because someone determined that we could make more profit having a catalyst driver than we could without it. So that's sort of the main reason. And the other reason is sort of more historic. So you know, the open source driver is something that, you know, it was around before AMD was really actually actively supporting it and working on it. So it's sort of always been there, and it's just sort of grew and grew. And especially recently, we've been putting a lot more effort into it, and you know, that's why we've seen all these new features, and there's been a lot more interest in it. So it really comes down to just different use cases, and you know, we're a business like everyone else. We have customers with different requirements. So there's that, and also with the closed source, we can reuse stuff from Windows. So you know, there's some less cost in doing that because we have, you know, a lot of stuff that has been validated on Windows. So there's some reasons to have it around. But we're definitely excited about open source driver.
You have to develop two versions of the same thing.
Yeah, I mean, you know, that's that's a good point. But again, you know, sometimes there's people have different requirements for what they want in a driver. So yes.
I'd add a little bit to that. I mean, the history part is important. When at NetAPI, I guess, first started doing Linux drivers, it was really focused on what we call a workstation market, the high-end graphics customers. There's a lot of workstation-specific optimizations in the closed-source drivers that we don't have in the open-source drivers. A lot of those optimizations, they're not, or even workstation-specific features. Those optimizations are not necessarily. I mean, people always think, okay, the catalyst drivers have more performance. It's not necessarily the case. They may have performance for that specific workstation application that has been optimized, and those are, I mean, very specific. You know, you choose a particular application stack, a very particular application on a particular OS is being certified for, right? Those kind of optimizations that are highly specific. I mean, there's a lot of code around them. It's not the kind of thing that the open source community is. It's not gonna, even if we wanted to release that, it's not the kind of thing the open source community is going to be that welcome to, right? You know, very, very large amounts of code. You know, that serve to meet the needs of a very small number of users, right? So, and the sharing with Windows for those workstation-specific optimizations obviously is important to be able to leverage that.
Yep.
So I want to test my understanding. My understanding was that there's certain proprietary things in there that you can't release, like, for example, I don't know, it's a decoding of video formats that take patent licenses or have trade secrets in them and so on. Like I know there were some things in the Catalyst driver that were not, historically, I don't know if it's still true, things like for video output and so on. How much of that is there? Is that all gone now?
Yeah, Tim can probably answer that because honestly, I don't really know much about the Catalyst driver and all the features it supports. So I'm not sure what there is, but we do. I mean, we do sort of, like I said in the presentation, you know, things like video decode and video encode. We do have support for those in our open source driver now, and historically we did not. So those are things that are new in the last 1 or 2 years.
Yeah, I mean, there are certain pieces of intellectual property where there are concerns around you know, patent activity, obviously, and those types of things. It's difficult for us to reuse. There are cases for us to release as open source. There are cases where we have licensed third-party IP that we don't have a license to release as open source. So obviously we have to keep that in closed source. I think over time, our hardware designs have gotten a little more friendly towards open source. So, for example, we may have features in the hardware that are specifically designed around content protection mechanisms for Windows, and maybe in the past those features haven't been clearly separated from. You know, they relied on more user space obfuscation type techniques, and they haven't been clearly separated. You know, so you might have the same register that has programming information related to content protection as well as, you know, other general techniques, right? So it's been hard to release that kind of stuff. Over time, our hardware design has gotten better with separating those things. Things like security is handled by specific security processors. So over time,
So for an example, I don't think it's legal for an American, and probably not a Canadian, to play a DVD movie on a Linux computer. And I don't know where you're breaking the rule. The DCSS, I think, is one part. Is that embodied in your hardware?
So that's a lot, I mean, there's nothing in our software for DCSS. I mean, I think the one example that comes up would be things like H.264. We're very careful, our open source licenses say very carefully that, you know, we don't grant you an H.264 patent license, for example, right? It's up to people to ensure that they are appropriately licensed, right?
So I think that could be an added value of yours, that when you buy the hardware, you get the license to use it to do that. But anyway, that's a whole different
Yeah,
discussion.
unfortunately, I mean, I think we would like to be able to do that, but the patent, the NPLA, for example, they don't license things that way, right? They don't like to give you a blanket hardware license. It's more per application. So tracking things is pretty tricky.
Yes.
So first I want to say I really like your Radeon drivers, and my question is kind of a little bit long. So I've had some experience. So basically I tend to factor in the graphics card that I'm going to choose when I buy a new laptop or buy new hardware. And I'm saying that right now I have very old hardware, very old. My experience has been that Ubuntu 12.04, I had a better performance with the Catalyst driver for an HP 4250, I think, like, you know, really old, right? It's old, right?
Yeah.
But then when I installed 1404 Ubuntu, I had better performance from the open source Radeon drivers, like it was kind of locking up you know, the Catalyst driver. The Catalyst driver has not been updated for a long time. Now, the question that I want to ask you is, and I heard you bring up this in your talk today, is also the thing of reverse engineering. And for me, that's an area that I would say is kind of a gray area for me, because, you know, when you talk about reverse engineering, you're essentially doing something which already there's some POS that I have agreed to not to do, and just I clicked on something and then I don't want to contribute to, let's say even if I want to, like it would be waste of my time if I'm going to spend, but I see a lot of you know, benefit in actually supporting, let's say, the Radeon driver going forward. Now I understand legacy hardware is something that's gone away, like I mean, really my laptop is not going to be the future, but let's say if I'm going in the future to buy a laptop right now and I want to contribute to the Radeon, you know, the Radeon driver, I'm kind of confused as a company now. You are on one hand having the open source community and you're also having the closed source. So I really, you know, I don't know whether I'm making my question clear.
I was saying if you, like, what hardware should you choose if you want to?
Yeah, so like, let's say I decide on AMD, like you leave aside NVIDIA right now, I'm not going to get into the NVIDIA, but even as an AMD client, sorry, an AMD customer, like you have two drivers that you constantly keep going, and obviously, let's say for some reason you want to keep Catalyst going because it's proprietary, so you lock up some features and all that. But then the Radeon is, so essentially what I would do is, I would download the Catalyst and reverse engineer it, put it into Radeon, and that's, you know,
okay, yeah,
all the reverse engineering. Like I'm getting confused with your talk.
Okay. No, I understand what you're saying. So we actually produce specifications for like programming, writing drivers for our GPUs. So if you want to add a new feature to Radeon, you really there's no reverse engineering necessary. We have documents that are available that you can look at that explain how to program the
So that would be clean room.
Yeah, we have all the documents are freely available, and it's actually what on the open source team, what I use most is our open documents. That's what I use, you know, my main reference. So those are all available for anyone, and anyone can look at them yeah, write the drivers.
It was the case that people had to reverse engineer HDMI sound output a year or two ago, I think, wasn't it?
That's true. Yeah, that was a while back, I think.
Well, like I seem to remember over the last 10 years, AMD has had an internal struggle with its lawyers about what it could release. I mean, it went on for years, I remember, the little emissions seemed to indicate that. Is that over, or is everything open now?
So I know we support, there's HDMI audio support in our drivers for certain chips. I don't remember whether was from the contributors who did reverse engineering or something we had done. I don't remember who did that work.
I mean, my recollection is that a certain amount of reverse engineering was done, and we then released further documentation, and now it is documented, and then the implementation was completed. I think people, if you read sites like Phoronix, people always have this sense that there's some kind of a fight going on with their lawyers, right? I mean, their job obviously is to protect the company, and these engineers working on this stuff have to operate in the best interest of the company as well. Some of these issues are tricky, right? And they don't take time because we're fighting amongst ourselves. They take time because they're tricky, right? And generally speaking, we ask people, just to be patient, right? We are trying to do the right thing. And I think that, when you see all the stuff that we put out there, you see that, there's the evidence that we are trying to do the right thing, right? But sometimes it takes time and longer than we would like it to take.
Absolutely, my comment sounds negative. My positive thing is there's nobody, as far as I can tell, nearly as open as ATI in the video world. Intel is a different model, and they're very open in a different way. But I really appreciate what ATI has done. I always say you can do better. I say that about the world I live in. Linux can do better.
What support for virtualization? You send Tom 0 or?
Right. So in our current GPUs, all you can do with virtualization is PCI pass-through. So basically, you can have a virtual machine that accesses the host GPU through pass-through, but then the GPU is unavailable to the host. So that's really the only kind of virtualization you can do. And our current chips don't really support having 5 virtual machines use the same GPU.
Yeah. And about GPU, is there any other? Are you enabling any other functionality with the GPU? I'm just thinking in terms of either for hashing SHA-256 or any of the other algorithms.
Yeah. So if you're implementing those using OpenCL, I'm sorry?
Can you repeat the question?
Sure. So the question was about, I guess, different GPU applications like hashing and other things. So if you're using OpenCL, that's the one API that we do support. And so things like, it's sort of hit or miss right now what works, but definitely things like hashing, like Bitcoin mining, for example, that works well. I've tested some password crashes; those work pretty well. So yeah, those are the kind of things you can do right now with our drivers.
Tom, thank you.
Thanks.
And next up is lunch. Just up, down to the end of the hall, and then cross over to the cafeteria area, and there's a hot lunch for us.